Okay, so today I would like to present to you our work on an SMT theory of fixed point arithmetic. I'm Tanson and I'm a student of Sonny Rock America at the U of Utah. And firstly, we want to quickly go through the motivation of our project. So as you know, the floating point arithmetic can be very expensive in terms of performance and power consumption. And so it leads to the fact that some platform like mobile phones, video game control, or digital controllers, and recently machine learning. They tend to use fixed point as an alternative to floating point due to its simplicity. And there is some field like medical or car control or robots that use fixed point based system. They need so that it's really safety critical. So they need a formal verification of floating point. And we know that the SMT theory of floating point have been formalized in SMT-lib and actively researched and applied in a lot of ways. So we want to do the same thing to fix point for the same purpose. And first of all, we will go over the overview of fixed point number. So the structure of fixed point number is just a fixed size bit vector with a certain number of bits used for the fractional part. So we can denote TB is the total number of bits and FB is the number of fractional bits. And the value of fixed point is exactly the value, the integer value, the bit vector represent, then divide by 2 to the power the number of bit vectors. So kind of it's really similar to the way we write numbers on binary, I mean fractional number on binary. So we can, for example, so TB is 4, FE is 2, and the bit vector represent the number 14. So the value of the fixed point number is 14 over 4, means FB is 2, so it's 3.5. And similar to integers, fixed point number can be psi or unpsi, and if it's psi, we represent it by 2 complement. So we can see the same example where the bit vector is the same, but if it's psi, so the integer is represented is -2 now, and the value of the fixed point is minus 0.5. So what is the contribution of our project? So we have introduced and formalized the SMT theory of fixed points. So we define the syntax, define the semantic, and we have implemented the 2 seasons procedure for the futures. Means we encode it into the 2 existing theory of SMT-lib, the bit vector theory and the real theory, and it make it publicly available. And we have performed some experiment on several SMT solvers, and yeah, and we have some case study when apply our theory in neural network. So for the syntax of fixed point number, we define 2 separate structs of fixed point number psi and unpsi, and we have 2 separate constructor for them from a bit vector. And for its arithmetic, so the result of the operations like the addition, subtraction, multiplication, division depends on the 2 concepts, which are overflow mode and routing mode. And so the overflow mode handle the outbound value, and the routing mode handle the extra fractional bits. And we also define functions for those operations. So we can see that multiplication operations should be like what we show here. We need to input the overflow mode and routing mode as the parameter or the input of the function. And we also define comparison and conversions from different types, different structure of fixed point, and from fixed point to real number. For the semantic, so most of the semantic, all the semantic is defined based on real number for clarity and convenience. So comparison of fixed point number is just compare reason of the real value they represented. For the arithmetic operator, so firstly, we perform the calculation in real for for the value, and then we convert the real value back to the fixed point value. And how we convert it? Firstly, we have to route it to exactly FE fractional digits, and then we perform overflow handling. So we have to overflow mode means saturation means if it's outside the bound, just put it to the bound. Greater than max, then it will be max, and less than min, it will be min. Wrap around means we doing the modulo arithmetic, like that of integers. Here's a quick example. So we want to do the multiplication of the two numbers here. And firstly, we calculate into in real, and it's pretty long. And then we have to trim down the fractional bit. We just keep two, so round up or round down when we get different results. And then because the number is outbound, so we have to do overhandling. So if it's saturation, so it's pretty big to store in the bit vector, so it must be at the maximum number. And if the overflow mode is wrapping around, then we trim down several most significant bit, just keep the 6 less significant one to keep the modulo. For the implementation, so we have encoded our theory into two existing theory of SMT-lib, the bit vector and real. When we do the implementation, division by 0 is considered, but it's too detailed to mention here. And we use PySMT's framework for our project. And here's the link of it on GitHub. For the experiments, we have converted 218 SMT-lib QEPI benchmark into fixed point. It means 1 to 4 for each combination of overflow mode and routing mode. We have 2 overflow mode, 2 routing mode, and so we have we multiply it by 4 cases, and we try it for many solvers like Pulector, CPC4, Matiev, YES2, and Z3, and also do 2 case studies on neural network. And here's the result. So so our first observation is that if the overflow mode is wrapping around, then there will be significantly more timeout for real encoding than bit vector encoding. As you can see, the 2 red box here, real encode has significantly more timeout. The reason behind it is when we convert into real, there must be some real to int function call for the modulo operation. So it's make the function much more complicated. And the second result is that we can see that each solver has strength and weakness. So when we see the red box here, so the table show that the number inside the table is the number of benchmark can be solved by the row, but cannot be solved by the column. So each column have a significantly number of benchmark which cannot be solved. So we know that we have to combine several solvers together to get to cover more benchmark if we want. And we have done 2 case study, means we apply the SMT theory to verify several characteristics of 3-layer neural network and the ReLU 7 activation function. Like this one is a card phone controller. We want to find whether when will we always turn left or always turn right due to several input value. And the second is just student score predictor, 2-layer network, and we want to see whether the 2 predictor has a certain output discrepancy, and this is 3-layer neural network too. And here's the 16 and 1 is the size of neural networks. So that's some application of our implementation of the theory. So thank you for your attention.